an example, consider the uniform distribution. Suppose you have a random variable, an example of a method of moments estimated. Suppose you have a random variable that's uniform on the interval from A to B. B is strictly greater than A. So what's the area under that density, that uniform density on the AB interval? 1. That is 1. So A is the lower limit of the random variable, and B is the upper limit. The mean of a uniform random variable is equal to what? Stated in terms, and those two parameters define the uniform distribution, A and B. That's all you need to know. If the random variable is uniform, you need to know the lower limit and the upper limit, right? So the first moment, the first population moment, is equal to what? Let's get this torture this out of Hillary. So Hillary. Yeah, so it's A plus B over 2 is the first population moment. And Hillary's found it in your notes. So how about telling us what the second central moment is for the uniform distribution? B minus A squared over 12? Or B squared minus A squared? Okay. So that's sigma squared, right? And we just decided that mu, the first moment, is equal to A plus B over 2. So if we have a barrel full of uniform random variables here in the front of the room and we take a sample, could we construct method of moments estimators of A and B? Yeah. Because we can use X bar to estimate, or we could use mu hat, the sample mean, to estimate the population mean, and we can construct a sigma squared, so we have a number, and we discovered maybe for our sample we got 5, and for our sample we got 14. So now we have two equations and two unknowns. And we solve the two equations for our two unknowns, and that's our method of moments technique for estimating A and B. And you can do that for any distribution. This is important, by the way, in finance, because in a lot of financial econometrics, you end up having to use method of moments estimators. I don't have an exact example offhand because it's not my area of interest, but I know that that's one area in which method of moments estimators are used. And they also are used in macroeconomics quite often. They're used particularly in dynamic models. There's a lot of dynamic modeling in finance, so that's why they come up. In dynamic modeling, it's very awkward, and there often are not closed-form solutions for least squares estimators in dynamic models. So you rely on the method of moments instead. Another estimator that we use from time to time is least squares. Robert, what's the idea behind least squares?
It's a model where you're attempting to explain something, explain a variable with the least amount of variance. And so what you do is you find the difference between the value and the real value. You calculate some of the square that difference and you add up all the square differences for the whole operation and whichever one it believes.
We want to pick as our estimator, that estimator, which makes the variance of our estimator as small as possible, or which minimizes our squared errors, our sum of squared errors. So we're going to do a lot more of that, so we're not going to spend much more time on that. And I already told you that a maximum likelihood estimator is that guess for the population parameter, which makes it most likely to have seen our sample. So we're going to let Hone revisit the king. So Hone goes to the castle. The king is on his throne, and he's got the same urn there with numbered balls next to it. And there's a large number of balls in the urn. Numbered, and I tell him now that the balls are numbered consecutively. 1, 2, 3, 4, so on and so forth, to whatever the greatest number of balls in the urn is. And I tell Hone, actually this example has a lot of value because it illustrates two ideas. So I tell Hone that if he guesses the number of balls in the urn correctly, he gets to marry the princess and live happily ever after. If he guesses the number of balls in the urn incorrectly, he gets fed to the lions. Got the idea? So what's your maximum likelihood estimator for the number of balls in the urn? The number displayed on the ball that you pick.
Can I get a pen on my card now?
Yeah. Good. Can you tell Hone why he's right? Is that the rule that you would use? The maximum likelihood rule? So you come to the castle, and the king is on his throne. Beautiful princess. You want to marry the princess and live happily ever after, and there's an urn full of numbered balls. And Hone says that the maximum likelihood estimator for the number of balls in the urn is the number on the ball that you pick. Are you going to use that rule?
Well, right now, the condition like we definitely that's why the I don't know how to gauge the system and the additional
Are we talking about the number of the balls in the urn now? I thought we were talking about the first one with the average, this one.
So now we're talking about the number of balls in the urn. It's a little bit easier problem to do.
So why did he pick the number on the ball?
That's what I asked you guys. Want to take another shot?
I've only seen one ball, and I have to...
You're only allowed to pick once, and you can hear the lions in the dungeon. They're down there roaring because they're really hungry.
Okay, so as far as I know, I've only seen
He
one
reaches
ball.
into the urn and he swishes his arm around until he knows that there's a whole bunch of them. There's not just one. There's not just two. There's not just three.
Oh,
He's
okay.
pretty sure that there aren't just 5. He's pretty sure that there's a large number. He's swishing it around and he's thinking to himself, what number am I going to guess? What number am I going to guess? And he says, I'm going to guess whatever number is on the ball that I take out of the urn. And he takes the ball. He's still got his eyes closed because he's praying. God, I hope I'm right. God, I hope I'm right. He takes out the ball and he looks at it and he starts to weep. So why is he weeping? He pulled the ball out of the urn that had the number 2 on it.
I don't know.
So once he's seen the sample, what's he going to do? There's a difference between the estimate and the estimator. The estimator is to choose as your guess the number that you see on the ball.
It's a formula you use. So that's
So right, the estimator is a formula, is a rule for guessing, making a best guess for the unknown population parameter.